Growing up, my grandma always told me that the land took care of us and it still is taking care of us, and it never asks for anything back.
It is a way of life to always honor the environment. It's not something that you just can turn on and off. It's a living daily lifestyle.
And that acknowledgement is a way to acknowledge that we're coexisting in this land with the native people, and we should acknowledge that this is actually their traditional territory. But at the same time, we are all guests to this land.
The land plays a big factor in who we are. That's what makes us strong. That's what makes us strong people.
Good evening. On behalf of Calgary Public Library, I would like to welcome you to tonight's program, Young Stars Amid External Radiation and Colliding Clusters, which is presented in partnership with the Royal Astronomical Society of Canada. As always, we will first hear the presentation and then have time for the questions. Please feel free to submit your questions during the program through the Q&A feature. And if you have any technical problem, please send us a message through the chat. And now I would like to ask Simon Poole, the president of Calgary Centre of Royal Astronomical Society of Canada, to take over. Thank you.
Thank you so much, Sorka. I'm just going to start my screen share. And we'll get going. So good evening, everyone, and welcome to the May General Meeting of the Royal Astronomical Society of Canada's Calgary Centre. We are one of 30 centres across the country created to enhance understanding and inspire curiosity about the universe through public outreach, education, and support for astronomical research. You do not need to live in Calgary or even in Canada to join our centre. If you like this program and would like to support our nonprofit organization so we can continue to have more events like this, please don't hesitate to join us. Information about joining us can be found in the chat window. Your membership comes with the world-renowned Observer's Handbook. There's also a US edition for those at lower latitudes. Also with the membership comes a subscription to the premier night sky magazine Sky News and the Journal of the Royal Astronomical Society of Canada, which contains the latest research into various astronomical topics. You will become a member of a community of professionals and amateurs who share a common passion for the night sky. Join us for online social events, star parties, and once the pandemic goes away, have full access to a local telescope rental program to see the night sky with all sorts of great equipment. The Royal Astronomical Society of Canada also offers great observing programs where you can earn certificates and pins by finding a certain number of great objects in the night sky. As for Centre News, we will be continuing our Parsec program next week for those Calgary Centre members who are interested in community science. Parsec stands for Promoting Amateur Research and Scientific Exploration of the Cosmos. This program allows Centre members to research and collect data using their own equipment and contribute to journals and databases around the world. We will be hosting Richard Harshaw, who will give an instructive lecture on how to measure double stars. Learn how to get involved in community science from your own backyard. And if you have any questions or are a Calgary member who would like to join this program, please don't hesitate to email David Brown at the address provided in the chat. Over the next month, we have a couple notable things to mention about the sky for the casual visual observer. On May 26th, just coming up next week, there will be a perigean moon, and a lot of people like to call it a supermoon, but astronomers tend to not to like that term because there's not too much super about it. It just happens to be when the moon is kind of close to the Earth in its elliptical orbit, and it it's typically larger than normal, but it's very difficult to see that. But also during that full moon, there will be a lunar eclipse, and that total lunar eclipse will occur on May 26th, and it will be visible from Canada, from much of Western Canada, with a partial visible across the nation. Just half a lunar cycle later, and it will be there will be an annular solar eclipse, and it will be annular because, well, we had the super moon, full moon, so it's going to be kind of a micro moon, so it's not going to fully cover the sun. So we're going to have an annular solar eclipse, and that will be visible from much of the north and in eastern Canada. We have some amazing astro imagers from southern Alberta, and they kindly have provided some images for us to showcase this evening. I'd like to start out with George Cavanaugh's Orion Nebula. This is just absolutely a beautiful image that he took of the Orion Nebula. You think like Hubble telescope here, but no, this is all done from the ground with amateur equipment. It's absolutely amazing. And Dalton Wilson, he was kind enough to provide this image of IC 410, and what an amazing image. Another one from George Kavanaugh, the Triffid and Lagoon Nebula. This nice, beautiful, wide field of some great nebulosity in the Sagittarius area of the summer sky. And here's Elephant Trunk Nebula that George has also provided. Some great work that these astro imagers do, and typically they do most of their work from here in southern Alberta. I just want to talk briefly about the Wilson Coulee Observatory. We're currently doing renovations on this facility. We have installed high-speed internet and cell booster, so you're going to get some great reception out there. And also, we're working on opening the high-speed internet up to club members, so look for that in the near future. Throughout the summer, we're also going to be renovating the exterior of the building, of the Sid Lee building, the clubhouse building, and that is slated to be done by the end of July. So we're really excited that we're able to renovate this wonderful building that all our members have free access to set up their telescopes in the field or use the large 14-inch telescope in the dome. It's a wonderful facility and a wonderful member benefit for our center here in Calgary. Some upcoming events on May 27th, we kind of already talked about it, but that's our Parsec meeting on measuring double stars. On June 7th, Don Haladiak will give his Radio 1 Astronomy, CBC Radio 1 Astronomy address at 7:36 in the morning. And on June the 8th, we've started a new program in conjunction with the Calgary Public Library, and that is called Starting Out in Visual Astronomy. And what this is a great program for those of you who are interested in learning more about astronomy. It's more of a kind of a hands-on approach to teaching you about astronomy. We'll show you how to use equipment. We will show you what's up in the sky at that time of the month, and we really want to have you have success in looking at the night sky and finding some great objects. So this is a wonderful program for you to join, and I believe that there will be a link in the chat to sign up for this program. So we had about 100 people come last month, and it was a lot of fun. There were some excellent questions, and there's a lot of people who want to get interested in astronomy these days. And this is, if you're not really sure how, this is a perfect way to learn more. So we really hope to see you there. On on June 17th, we will be hosting a full meeting dedicated to member showcases. This will be a member showcase social. So members of the Calgary Center will get together and we'll talk about what you want to talk about. Anything that's grabbed your eye in the last year, you know, that you want to talk about. If you did any traveling, I know it's kind of been difficult during the pandemic, but you know, some people have got out to some really good dark sites throughout Alberta, and if you want to share, please don't hesitate to let me know. So yeah, bring your astronomy stories and travel logs. And if you want to spend 5 to 15 minutes in a showcase, please email me and we'll book you into the program. And we'll have the chat and the mics fully open, so it'll be a great social event for RASC members. And the instructions on joining will be found in the June Star Seeker, so keep your eye out for that. So moving on to tonight, we're incredibly grateful to have an astrophysics PhD student with us this evening. Alexandra is a poet turned astronomer. Her first science course in college was quantum mechanics, which she passed and kept on going. She's now pursuing her PhD at Georgia State University, researching young stars in a moderate radiation environment and the collision of star clusters. And she's excited to talk about that here this evening. So please join me in welcoming Alexandra this evening. Thank you.
Okay, let's see. I guess I get going now. All right. So hello everybody. Special hello to all my Calgary friends in attendance today. It's been a while, but I'm still out here somewhere. So let's get started here. I'm just going to share my screen. And I'm going to tell you about all the cool research I'm doing. Thank you for the introduction. So here we go. So yes, I research young stars in an external radiation environment, and I'm also looking at colliding clusters. So let's first delve into what makes a star. So stars are made of gas, technically plasma, but yeah, in a general term, gas. And this is just a picture of the Orion Nebula. I admit that George's picture is actually much better. I may have to contact you later, George, because that was just a beautiful picture that you had there. But anyway, you may already know this, but yes, stars are made of gas. You start out with this big, just expanse of molecular hydrogen, and you wait for gravity to do its work. Let's actually take a look at that. So this is just a schematic, but you have your large molecular cloud like this, and over time, its self-gravity will cause it to fragment and condense and get denser and denser and denser until finally you'll get some little dense balls of gas, and you'll have a protostar buried somewhere inside that gaseous cocoon. So yeah, you don't really see it too easily. If you get infrared, you might see it, but you'll just have to trust me. There's a baby star in there. And eventually that star will, it will accrete some of that gas in its cocoon, and it will tend to be spinning pretty fast. And some of that angular momentum will flatten all that extra gas out into a disk. Then you get this nice object called a T Tauri star, which is just it's a baby star surrounded by that formative gas and dust. And it's in that disk that planets will actually form, hence the name protoplanetary disk. So eventually, it takes a little bit of time for that disk to eventually go away. Usually they live about, I don't know, 3 million years, give or take. And after that point, the star's own light will tend to disperse the disk, leaving behind just the star and its solar system, essentially, of planets and comets and other objects. Okay, so there it is. This is what's called a main sequence star. It's starting to fuse hydrogen. That's what makes it a star, technically. And it's surrounded by all those little planets that it managed to form in that disk that it has since dispersed. So that's sort of the normal way that a star will form, and it'll tend to have those planets form. They're actually quite common. It's quite common to form planets, we think. Still working on that. But that's not really the whole story. That's just a zoomed in view of just one star, right? But it formed from such a huge, massive gas that these clouds actually tend to fragment into several such dense cores, and thus stars tend to be born together in clusters. So it's not normal to really find one by itself. It's normal to find them in groups of 100 or even 1,000 like this. So here's a star cluster. All right, so, and even clusters tend to not necessarily be alone. So we have to ask ourselves, are stars affected by the other stars in their cluster? And even these clusters, sometimes they're forming in, for example, the plane of our galaxy, where there's a lot of gas going on. Anybody who's seen a picture of a spiral galaxy will know there are those very gaseous spiral arms. So there could be not just one star cluster, but many star clusters. So we have to also ask, are clusters affected by other clusters? My thesis research shows that yes, in fact, they are. Stars are affected by other stars, and clusters may even be affected by other clusters. Let's first look at how stars can affect other stars. So we have here another star cluster. And let's think about for a second, what kind of stars are in that cluster? Most stars tend to be small, cool, and dim, smaller than our sun, in fact, and even a little bit cooler than our sun. It's still hot to us, but it's cool for a star, okay? And yeah, that really accounts for most stars. Most common star is just a little red dwarf like this. But every once in a while, you get a big, fat, giant, hot, bright blue star that just pumps out a ton of UV radiation. And you guys all know what it's like when you're out on just a hot summer day on maybe like the 10 days of the year during which Calgary is hot. But yeah, you know how it feels, right? You feel that sun beating down on you. So we know how that feels. Well, how must that feel to a star? Imagine being just a little baby star somewhere out in space. You have your planet forming disk surrounding you. You're just starting out in life, but you happen to be in a cluster where you're near some hot star, even if it's 100 light years away or so. That's still close enough for this hot star to pump out a ton of far ultraviolet radiation that can just come your way. What happens? Well, that nice little planet forming disk you have might actually erode just from the sheer light pressure and the interactions that happen from that intense radiation. So that's the theory, right? So a good place to study this is in the southern sky. This is a picture here of the Milky Way, as well as the SMC and the LMC. We got this bright star Canopus, and Sirius is somewhere off of frame, somewhere up above the rest of this picture. And then here, this reddish glowy thing, that is called the Gum Nebula. It's a very diffuse, spread out nebula, believed to be powered by 3 particularly hot stars. And there's the little triangle they form. So that's sort of the heart of the Gum Nebula. That's what's powering its faint glow, its H2 region. So let's take a closer look. So this is a moderate radiation environment because of those 3 hot stars. We got Zeta Puppis, Gamma Tuvalorum, and until recently, the star that blew up and made the Vela XYZ supernova remnant. And there are also some OB2. There's some OB regions. There's some O-type stars, B-type stars. So collection of hot stars, but the hottest ones are these 3. And of course, it's really just the 2 at this point because one of them blew up. But there you go. All right. So I'm looking at a particular cluster somewhere in the northern region. That was my first area of study. You see this collection of stars over here on the right? These are all pretty young. They're as young as 500,000 years, maybe a couple million years, but that's pretty young for a star. That's young enough that they're still expected to have those planet-forming disks surrounding them. Very, very young stars. And the way I studied these was using the Keck telescope. I did not go there myself. My advisor did the observing along with Lynn Hillenbrand, but I got the data. That's actually why I came to Georgia State, is I knew my advisor had that data and I wanted it. So here's what some of the data looks like, just so you can have an idea of what my day-to-day life is as an astronomer. Bunch of nice spectra, looks like a bunch of squiggles, but these squiggles can tell you a lot. So for those of you a little bit less familiar with spectroscopy, let's just take a quick look here. So here are 2 spectra. We have a small star and an even smaller star. Do you remember when I said most stars really are smaller than our sun? Well, that applies here too. In this particular little region, in this little tiny cluster that I'm looking at, it's pretty sparse. There are not really any hot stars. They're all quite a bit smaller and quite a bit cooler than our sun. But look at these nice spectra that they produce, these light signatures. As you can see, this is one for a really tiny star, an M dwarf, and this is one for a slightly larger but still quite small star, a K dwarf. And as you can see, these light signatures really do look different from each other. The bottom one for the tiny, tiny cool star actually has these broad troughs. These are actually from molecules in the star's atmosphere, because it's actually cool enough to have molecules. Any hotter, the energy would break those molecules apart, and that's why the K dwarf up there doesn't even have those. It doesn't have as broad dips. It only has some nice narrow ones, and those are just from individual atoms. This is all a bit of quantum mechanics, really, if you want to go into what's actually causing this. But the general idea is these spectra that we get from these different stars really do look different from each other depending on what kind of star it is. And they can tell us a lot about the temperature, the size, the motion, the rotation, all sorts of stuff about these stars. Also the age and whether or not they have a disk. And speaking of disks, that's what we're really interested in here. So here are some pieces of the spectra that look particularly at hydrogen gas. Hydrogen is the most common gas in the universe, so it's great for measuring all sorts of types of properties. And a big one that it's showing here is, well, first of all, these all look very different, don't they? So on the left, we have this, it's not even a dip, it's actually a mountain, right? It's emission, it's what's called emission. This is from gas around the star getting electrified by the star's light. And look at how broad it is. This is a huge signal from this hydrogen gas. So that's actually indicating a lot of gas motion, particularly associated with this young star accreting material from its disk. It's actually still building up its mass. It's this is very layman's terms, but it's kind of pulling some of that gas from its surrounding little gaseous disk and actually adding it to itself. It's still kind of feeding, if you will. Okay. So that's a very, very young star, still growing. When the star gets a little older, it will have still a little bit of a signal there, still a bit of emission in the hydrogen gas, and that's that little tiny spike in the middle. That's showing that it's not really accreting anymore, but it still has a lot of activity. It's still a very active young star. There's still a lot going on with it, still a lot of energy. And then eventually the disk goes away, the chromospheric activity calms down, and you get a trough like normal. Most features in a star tend to be these absorption features, these troughs. So these are the different types of stars that we can look at, and it's a great way to classify them. So that's one thing that I did for that initial little tiny cluster that we saw in the northern region of the Gum Nebula, is I just looked at all these H-alpha signals, hydrogen gas signals, and I actually picked, okay, this one looks really broad, it's probably accreting. This one's kind of narrow, still emitting, but it's probably just active, but not really accreting anymore. And some of them, not really much activity, it's just absorption. So this is actually a great way to actually tell how many disks are still out there, how many of these stars still have planet-forming disks. So let's compare two regions. On the left here, we have Taurus Auriga. This is a cluster that doesn't really have, it's a region that doesn't really have a lot of hot stars, so it's considered quiescent, okay? And this is in comparison to the Gum Nebula, which, as you saw, has those bright hot stars at its heart, okay? So that's a moderate radiation environment. It's not as crazy as the Orion Nebula, but it's still moderately irradiated, okay? So there we go, those two different regions. So then I went and actually counted how many of the young stars still have disks, still have accretion from these disks. And the normal number, if you can call anything normal, for a quiescent region would be about 50% of the young stars still have disks when they're about 1 million years old, okay? So that's normal. The disks will tend to disperse over time, of course, so we have to account for age. But yeah, these two are similarly aged. Then we look over at the Gum Nebula and that tiny little cluster I'm looking at, where only about 30% of those very young stars still have disks. So that's kind of low. And one must wonder why. Well, I suspect it's because of those that radiation environment, right? And you can see kind of from that little picture up there, that radiation streaming off of the hot stars at the heart of the Gum Nebula can strip these protoplanetary disks of these young stars. And that's what looks like is happening there. But that's just one cluster. It's called CG30 in case anybody wants to follow up. So obviously one cluster isn't really enough to make a statement in astronomy. So it's enough to write a paper about, but I got to find more of these. So next step was to just find more clusters. So how do you find more clusters? Well, some of you may have heard of Gaia. It's a great big mission. It's a space mission that went and found parallaxes, proper motions, all sorts of basic positional and kinematic data for a bunch of stars all across the sky. Really, really good data resource. Well, if you are a cluster of stars, means you're generally born together and you're moving through space together, right? So theoretically, you could just take some data and just look for little collections of stars that are in the same spot, same distance from Earth, and have roughly the same motion through space, because that means they're together. That makes a cluster by definition. So that's exactly what I did, and I did it the easy way. Really, anybody could do this. You could do this if you're like 5, you could do this. So you take a big swath of data from Gaia DR2 in whatever region you're interested in. For me, it was the Gum Nebula. And then you start just making some parameter cuts. You start saying, okay, maybe you're roughly anywhere from 300 parsecs to 400 parsecs away. Roughly, that's around where the Gum Nebula is. So you cut that. Let's see, did I do the motion cuts first? Oh, I did the motion cuts first. Oh, well, whatever. Anyway, you cut something, right? Maybe you already know roughly how your region is moving. And I had some idea of that. So I made some motion cuts, then I made some distance cuts. And as you can see, we're starting to get a little blob. Each cut that you make, you throw out a bunch of data that doesn't fit your cuts, and you just keep the ones that show up. This is color coded also for distance in this particular picture. So ideally, you're gonna, by making these cuts, you're eventually going to have emerge a little blob that's kind of the same color, adjusting for the changing of your distance scale, and is in kind of the same spot. And then you throw away some data that has errors in its measurements, and you get this nice clean little cluster. Look at that, we found one. Wasn't that easy? So I just did this throughout the Gum Nebula, and I found 8 such clusters. A lot of them have shown up in catalogs by now. 4 of them have been previously studied to some extent, but the other 4 have barely been studied at all. And really, most of these don't have a lot of data on them. Not a lot of pre-existing spectra. So I've actually been having a lot of fun getting new spectra of these and finding out about just the general properties of all these stars. So that's pretty neat. And one of the first things I wanted to look at again was those disks. So here are some more hydrogen gas signals. And as you may recall, the broad ones, the really, really broad ones are associated with the gas motion as the star accretes. So that means it still has an active accreting, possibly planet forming disk around it. And then once that disperses, there might still be small emission signals for just a little active young star. And then once that goes away, then you just kind of have a dip and then not as much is going on. So this is just a small selection. I have about 300 stars that I'm looking at right now, just across all these different spectra, just picking whichever ones I could observe with the particular telescope I'm using. I'm using Chiron spectrograph on the CTIO telescope, the SMARTS telescope in Chile, if anybody is curious about that, and I can tell you more about that later. But anyway, suffice it to say, some of the stars in these various clusters appear to have accretion signals, so they still have disks. So let's take a look at what they are. So as you can see, these particular 3 clusters here, these were the younger ones that I found. We got one for 9 million years, 6 million years, 7 million years. That's still pretty young for a star cluster. And then on the right column here, we have their disk fractions. So how many of the young stars still appear to have disks? 2%, 14%, 9%. That's sort of the ballpark. Well, when I compared this with clusters in quiescent regions, such as Taurus, Auriga, and other regions that were a little bit older, the quiescent region figure for this age range tended to be about 15 to 30% of stars still having disks. So the fact that I'm only seeing anywhere from 2 to 14 in this particular set that's kind of low. So even these other clusters that I'm looking at appear to have some sort of sign that the strong radiation from those hot stars in the middle of this cluster are perhaps stripping these disks early. So that's looking like it's really happening here. All right, so that's just that's one way that the stars can affect each other. Another way that you can check possibly for the erosion of the protoplanetary disks is it actually may affect how fast the stars spin. This is a little theoretical and a little bit preliminary, but theoretically, think about being a baby star and being surrounded by that big disk, right? You're going to interact with that disk. And the longer you have it, the more it's going to theoretically slow down your rotation. So one would think that if the disks were stripped early, maybe the young stars would have higher rotation than normal just because they weren't interacting with that big disk as long. So we measured the rotation of these stars, and this is just a plot of the cluster age versus the rotation speeds on the vertical axis for each of these stars. And it's also color coded for the type of star, since that will also affect rotation. And if we were seeing this effect from the disk stripping, maybe leaving us with faster rotating stars, we would expect to see more of the reddish and orangish dots higher up on this plot. And we see a couple of them, but I don't yet know if it's enough to prove this. It's not. I don't know if it's enough to really say much about whether or not we're seeing this effect. So maybe we're not seeing it so much in the rotation speed. More work's needed on this sector, but at least the H alpha stuff on the previous page, that was pretty telling. So we're gonna probably still pursue this rotation speed result, but it looks sort of null, even though the other result looks like it's positive. Well, that's science for you, right? It's always a work in progress. All right, so that's how stars can affect other stars. The hot stars can maybe strip the disks of baby stars. So that's the first section of my talk. The next section is, let's think about how clusters might affect other clusters. So plotted here on the right, this is just the positions of these two clusters. One's plotted in red, the other one's plotted in blue. These are two clusters that I found during my search. And I noticed one day, well, heck, they're lying on top of each other. That's sort of interesting. So then I made these histograms over here on the left showing distance and their motions in each of the dimensions. And what I found was their distances, see that upper left plot, their distances overlap. So that the purple part is where they overlap. So not only are they overlapping in the plane of the sky, so looking like they have similar RA and DEC, but they're also at a similar distance from us. Well, that kind of makes it sound like they're in the same place in space, doesn't it? So that's interesting. And then I said, okay, well, are they the same cluster? Maybe they were just actually born together and it's just one cluster. So I checked their motions. Well, their motion in right ascension, that's the upper right plot, kind of in the histograms, the upper right histogram, those appear to match, but their motions in the radial direction and in the declination direction, they don't match at all. So that means these two clusters are in the same place at the same time, but they have different motions. What this means is these clusters may have recently collided. That's the only way you can really get this situation, right? They're in the same place now, but they got there from different directions. So these clusters collided. So I decided to make some simple simulations. Here's one of the clusters. Bam, look at that. It gets hit by the other cluster, and that's something. Let's just watch that again, just because it's kind of entertaining, actually. This is just a simple linear extrapolation from the current positions in motion. So some of the contraction and expansion that we're seeing is it's not totally representative of the cluster. This should really be done as an n-body simulation with an integration through the gravitational potentials of each other and with the galaxy. So the more complex version of this simulation has yet to be made. But even this simple one, especially within a few million years of today, it shows that there's an interaction happening here. It might also help explain that, I mean, these are very elongated clusters. Maybe that's because of this interaction that they're undergoing. Let's see another view of it. Here's from the other cluster's view. There it is. Bam, look at that. So yeah, I've checked the literature. This has not really shown up before. I mean, there's really no reason it wouldn't, right? I mean, stuff in space can encounter each other, right? It's sort of a big place, so it's rare, one would think, but it can happen. And it certainly looks like it's happening here. Here's some more views. This is just a paused 3D rotating view. This is from today. And yeah, that's some significant overlap. The ellipsoids that I fit just sort of show the general position of these things. There is an artificial elongation in the X direction, the radial direction for distance, not just because of the proportionately larger uncertainties in distance relative to the other dimensions. But there still looks like there's some good overlap. And here's from the peak of the collision. This was about 810,000 years ago when I think the collision was at its height, when the centers of mass of these two clusters came the closest. They came within about maybe 20 parsecs, I think it was, roughly. And that's sort of similar to their sizes too. They're kind of 20 parsecs across, give or take. And once again, you can kind of see that artificial elongation in the X direction. So better measurements in the future will help correct for that. But in the meantime, here it is. And it's sort of neat, isn't it? So that was just the nominal values. That was just based on what did Gaia measure? What did I measure for the radial velocities based on those spectra that I got? What happens if you just extrapolate through time and watch it, right? So that's just the nominal values. To get a better idea of the statistics, I also did a Monte Carlo simulation here. So that's what this is here. I have several just results from my Monte Carlo simulation. For those of you who don't know what a Monte Carlo simulation is, basically, anytime you make a measurement of any property, for example, the distance to a star, there's always going to be some uncertainty to the exact amount. I mean, heck, even if you measure how long is my thumb with a ruler, if you measure with a different part of the ruler or even somebody else's ruler, or even you kind of say, well, how do I handle this squishy part up here, right? There's going to be some uncertainty to the measurement. You're going to be like, oh, it's a few centimeters, give or take. I don't know. I actually haven't measured my thumb. Maybe I should have done this first. But, it's like, what is that? 7 centimeters, give or take a centimeter? There's always going to be a little bit of wiggle room in your measurement. Always. There's always a bit of uncertainty. So what you do when you're doing this in science is you have to account for that. You have to say, okay, within this wiggle room, how likely is it that this encounter with these clusters actually happened? So one way to do that is you can do a Monte Carlo simulation, which basically just says, okay, here's your nominal value, right? And then you say, okay, based on my wiggle room, what happens if I just nudge it a little bit, just randomly, if I nudge the measurement a little bit within the uncertainty that I measured, and then I run the simulation again, and I watch my clusters collide again. How will it change? So that's what I did. And I nudged every single star a tiny, tiny little bit, and then I ran the simulation again. I did this 10,000 times. And here are the results. So let's look at the results. We have a few different plots to go through here. So let's just start with the middle one that's kind of dark purplish. It's the middle histogram. That shows the minimum center of mass separation of these two clusters. It shows the most likely separation. It comes out to about 19 parsecs, okay? And then we have some tails for the statistics, right? It's 19 parsecs, give or take a parsec, according to my simulation. Okay, and once again, that's similar to the size of these two clusters, so that's some pretty good overlap. Then we can also look at how many stars within these clusters came close to each other. And by close, I mean within a parsec, okay? So that's within a few light years. That's closer than the nearest neighboring star is to us, so closer than Proxima Centauri. Okay, I went and measured how many of how many stars tended to come within 1 parsec of each other, and it came out to about 55, give or take a few stars. 55 stars coming within a parsec of each other during this cluster collision. Now, none of them are going to hit each other. Don't get too carried away with the term collision. Space is still a pretty vast and empty place. So for a star to actually hit another star, unlikely. But for a star to pass close to another star, and maybe gravitationally interact with it and mess things up, that can happen. So let's look at the results for that. The closest any two stars tended to come to each other within this simulation was about 0.14 parsecs, which translates to about 29,000 astronomical units. So that's well within the extent of our, well, as far as just comparing it to our own solar system. Our solar system has what's called an Oort cloud full of comets and yeah, mostly comets, other debris, whatever it is, right? And that extends out, give or take 50,000 astronomical units. It's still a pretty rough number, but 29,000 astronomical units, that's the closest two stars tended to come within my simulation. That's well within the Oort cloud of the other stars. That's these two stars' solar systems essentially sweeping through the edges of each other. Okay, so that's pretty major. And another thing we can measure is what's called the impulse, which is just sort of the momentum imparted to a comet, for example, that's in that Oort cloud of the other star. This tended to be about 2.7 with a pretty large error margin, but it's enough to actually move things around. This could significantly affect the stars. This could actually shift comets' orbits out of the Oort cloud, maybe potentially into inner orbits. And then you got these comets that could come inwards towards any planets that these stars may have. And that could be pretty catastrophic. So let's think about that for a second. Oh yeah, first let's do the left plot. The left plot just shows where you are in the cluster kind of affects how likely you are to encounter another star. So this is sort of a heat map of interactivity likelihood. All right, let's think about those comets now, okay? So imagine you're on an exoplanet that's orbiting one of those stars that happen to have a very close pass to another star during this cluster collision. Because that's what really happens. The stars kind of pass past each other. They just pass each other, but they might pass close. So say you're on one of those planets of one of those stars that passes really close to another star. You're living your life. You're just on this planet. There's your star, that nice yellow one over there. Oh, look at that. What a nice star. And then all of a sudden, there's a new star in your sky. And you're just like, what's that? It probably shows up very slowly. Okay. It takes several hundreds of thousands of years for it to really kind of come to your knowledge. Probably somebody figures out and says, oh, wait a minute, my ancestor didn't tell me there was a star over there, right? And that's all fine and good, except that as these stars might pass close to each other, you might have your Oort cloud disrupted, like I said. So some of these comets that are far out in the outer reaches of your solar system might get dislodged from their far out orbit, and they might come towards you. So give or take a few million years for that comet to travel, you might get more meteors, you might get more meteorites, you might get some cratering events, you might even get some extinction level events with these increased impacts that you're getting. And especially with comets can be pretty big and they can move pretty fast relative to you. They are actually more likely, for any given comet that's coming your way, it is statistically more likely to cause an extinction level impact than your ordinary near Earth asteroid. So that's sort of scary, right? And this is just from these two clusters of which your star is a member, just passing through each other like this. All of this could happen to you on your little planet just because your cluster had a collision with some other cluster. So it's kind of scary. It's kind of crazy out there. It's tough to be a planet out there. And that was just for the two clusters. What I also looked at is I looked at some other clusters in the neighborhood. They might be interacting too. So this is also preliminary, this particular little movie here, but this is just the region around the two clusters that we see interacting. And yeah, they also appear to turn the same color and come right next to each other. They might be interacting too. So what this might mean is cluster interactions, even though they haven't really been studied much, they might happen all the time, at least in the plane of the galaxy where it's a little bit busier. So with that in mind, we really may have to take cluster collisions into account when considering how clusters, stars, and even their planets evolve, because they actually all exist together and it's a very, very dynamic environment. So I'll just leave this up. This is really my summary slide. So yeah, I guess that's everything. So I will now take questions.
Great, thank you. Thank you so much, Alexandra. That was amazing. I'd like to just put up a poll really quickly as you type out your questions into the Q&A, and we'll we'll ask you some questions. So yeah, if you don't mind filling out that poll, that would be great. That'll help us to present, to better able to present in the future. And yeah, please take your time to type some questions into the Q&A box, and we'll have a great Q&A session in a minute or so. So as this poll winds down, Alexandra, I'll start asking you some of these questions. Somebody asks, is it true our sun, our star, is 15 million degrees Celsius at the core, and how do we know that? And 5,500 degrees on the surface, and how do we measure that?
So both of those are true, and here's how you measure it. You have to kind of go into atomic physics here, okay? So the core, we estimate the temperature of the core from a couple different things. For one thing, in order to physically fuse hydrogen, you need it to be at least 13 million degrees, if I'm remembering correctly. So even just from that, because the sun is fusing hydrogen successfully, we know that has to be hotter than 13 million degrees. To get the exact temperature, it's never really exact, but we just sort of figure that out from the size of the sun, the approximate mass, which you can figure out from just how the planets orbit the sun. It's sort of a binary calculation. I think you have how to calculate binary stars coming up, and that should maybe give you a little bit of a clue as to how you would actually calculate the mass of things. Kepler's law will let you do it, actually. Kepler's third law would let you make the calculation for the sun's mass just based on how your planets move and how the sun moves a teeny weeny little bit. There's a way to do it. I think I actually even have that happen in one of my astronomy labs. It's not too bad of a calculation. It's kind of neat. Anyway, so that gives you the mass, and then you do a bunch of complicated calculations for the pressure and how hot that has to make it in there, and then eventually you arrive at some number, 15 million degrees. So that's how we know that one for the core. It's kind of a combination of atomic physics and just, yeah, gas physics. A lot of ideal gas law, bit approximate, but it kind of works. And then for the surface of the sun, yeah, like I think your estimate 5,500, whatever it was, that's roughly correct, right? I think I usually hear 5,777, but I think that's just because it's kind of a cute number. That's never exact either, but the way you figure that out, this you can do with your spectroscopy. So let me see. Can I get rid of this poll? I'm gonna move the poll. Okay, so let's see. I hope I didn't kill everything by moving the poll. I hope it was okay. Anyway, so let's stare at this for a second. So when you look at lines, these special little spectral lines, this is atomic physics giving you information, okay? So different types of atoms, for example, hydrogen or calcium or any other of these, sulfur, any of these other atoms that show up just throughout the star, they will be ionized at different temperatures, and they will tend to emit and kind of deionize at other certain temperatures. So based on which lines you see and how strong they are relative to each other, you can infer the temperature of that star. And that's just by comparing to laboratory results and stuff. You can kind of figure out, okay, this is how hot this has to be ionized in the first place. And what ionized means is that means you have, let's see, you're kind of missing an electron, and then you have a space for one to come back and then emit energy on its way down to what's called the ground state. So that'll happen at different temperatures. I hope that kind of clarifies it, just based on what atomic energy emissions and absorptions are happening, you can actually infer the temperature.
That's awesome. Somebody asks, is the rate of star formation slowing down?
Yeah, in general, yeah. And that speaks to the eventual heat death of the universe, which makes me so sad because I really like stars. But yeah, so in the beginning, when not too long after the Big Bang, when things were still pretty compact, right? Hopefully all you guys know about the Big Bang generally, right? It started as a singularity, and then the inflation happened. Well, the Big Bang happened, and then inflation happened. And then all of a sudden, whoa, you have this universe, right? So that's been expanding. Okay, that's been expanding and expanding, and dark energy seems to be the culprit. And what that means is, back in the early days, things were all kind of closer together. It was still a big universe, but in general, the matter that is in the universe was just in a smaller space. And if you're in a smaller space, then you theoretically have more gas that's in a denser area, or it's denser where it is, and then you can form more stars easily just because you have more gas in a smaller space, right? As things expand, that gets harder. And the dense pockets of it sort of get almost used up, right? So they'll form some stars. Those stars will blow up and they cause new stars to form. But as all that's happening, gas sort of gets emitted out into space and kind of travels out by itself eventually. And everything's getting farther and farther apart, such that eventually, yeah, you have less material and it's in a larger and larger space. So it just gets harder to form stars eventually. So yes, that was the long answer to your question. And I could have just said yes, but yes.
Oh, I appreciate you going deep into that. That's awesome. Somebody asks, how is a star's age determined?
Ooh, that's fun. Okay, so there are a couple different ways of doing this. I actually think I cut that slide, but I could go find it. Let's see. Where did I put that HR diagram? So there are a couple different ways. Oh, one of them I can show you because it's actually right here. For young stars, you see this? This is you see that second column that says Li1? That's lithium, okay? Lithium is an atom that, as far as a star is concerned, is easy to squish into other atoms and get energy out of. So stars tend to use up their lithium pretty quick. And if you're a young star, and if you're a relatively small star such that you have convection happening in your layers of gas, the lithium signal will tend to get pretty small pretty quick within some several million years, depending on what kind of star you are. But yeah, it gets used up fast for a star. So what this means is, if you see lithium in your relatively small star, if you still see a signal at this exact color,
you might have to share. You might have to share your screen. It's not coming through for some reason.
Oh, weird. Okay, let me redo that. I thought I was still sharing. There we go.
There we go. Perfect.
Great. Okay. Yeah, I thought I was still sharing. Maybe I was not. Anyway, see the second column? That's lithium. And see that little dip in that column? That means lithium is present. If you see that absorption feature, that means there's an atom there that's eating up that exact wavelength of light. And the deeper it is, the more lithium is present. Because stars tend to eat through their lithium pretty quick, and then they run out of it, it's normal for you to look at a star that's really anything like adolescent and up. You'll tend to look at it, if it's an older star, it won't have any lithium. If it's a small star, things get a little complicated for the bigger stars just because they're not as convective, but we'll ignore those for a second. Looking at the lower mass stars, if you see lithium, that means it hasn't used its lithium up yet. That means it must be young. So that's one way of telling a star's age. The other way is to get an HR diagram. And for this one, you're going to have to, let's see, I don't know which part of my screen it is sharing, but let me just see if I can pull up a plot that I have lying around. I have a whole bunch of these. Let's see, where's my HR diagram? Basically, you plot your stars to show color versus brightness, and they tend to form a certain pattern. Give me just 1 second. Where did I put all of those? Okay, they must be in my paper. I'll go get it from my paper. I have a Chiron proposal that I think I lumped them all into. Chiron. Does this have it? Yes, okay, I got it. So let me double check my screen sharing. Let's switch over to this. Does everybody see this mess of plots?
Looks good.
Good, okay, so these are HR diagrams. And so it's basically the color of the star, which is associated with its temperature on the horizontal axis, and then the brightness of the star on the vertical axis. And they'll tend to lie along what's called a main sequence, or in this case, a pre-main sequence. That sequence, the brightness relative to the color for a star tends to lower over time until it stabilizes on what it's called the main sequence. What this means is if you plot all the stars in a cluster and they are bright for their color, that means you may have a young cluster. Okay, that's sort of and you plot what's called isochrones, little theoretical models of where the stars should be, like how bright versus color they should be at different ages. And from that, you can kind of figure out, oh, it looks like this one's, say, 7 million years. It looks like it's lying along that theoretical isochrone. So you can kind of guess that way. So those are the two different ways to figure out the age of a star. There's some other ones too. And there's specifically, I guess, the main sequence turnoff if it's like adolescent to medium age. But yeah, those are the two main techniques.
Awesome, thanks. Oddly, I have a question that came in on my cell phone. Somebody texted me a question. Is there any evidence that supports repeat interaction between these clusters? And if so, is there any evidence of a central gravitational influence that these clusters could be orbiting?
Oh, okay, let's think about that. So that would require the true n-body simulation, right? So that would require me to actually get the whole galaxy involved, because the clusters are orbiting around the galaxy. Everything is. We are too. Everything in our galaxy is orbiting around that black hole that's in the middle. So a more realistic simulation would account for that, and we would actually see some of that motion while they collide. That will probably actually make our collision counts go down a little bit, but probably not too much, because the span of my simulation, it's only a few million years. So, well, where the interaction really happens, the interaction only takes about 2 million years. That's not really that long. So there would still be that interaction, but yeah, accounting for that will change things a little bit. What was the rest of that question?
Just if there's any evidence of a central gravitational influence that these clusters could be orbiting, like would they collide again, sort of idea?
Oh, will they collide again? Possibly, probably not is what I would say. It's sort of unlikely. It would take a really long time, and that's because in the plane of the galaxy, sometimes things do this. They kind of interact with the plane itself, where a lot of the material is. So they'll kind of bob up and down a little bit as they go around. So maybe, depending on maybe one's like catching up with the other one a little bit. And then if you wait forever, they'll go all the way around again several times, such that eventually they end up on the same side as each other again. Because for a long time, it'll kind of like trail each other like this, and it'll be really kind of slow. If you've ever watched one of those, what is it, the cyclorama or something, when you got two bikers cycling around this ring trying to catch up with each other, right? They go around a whole bunch of times before one of them finally catches up with the other one. I would imagine that's what would happen with these clusters eventually, but the chance of them actually colliding again when they eventually catch up with each other, very low.
Awesome. Somebody asks, I don't understand how a minimum separation makes sense. Surely the stars might come closer than that, or is something preventing them from approaching more closely?
Okay, so minimum separation is just really my name for what I'm measuring. And that's because it's like the closest any two stars come to each other. And that's because in my simulation, which has all these positions of all these different stars, I'm really just sort of saying, okay, in this one simulation, because I do 10,000 of them, in one of them, I track, what is that, like 400 stars or whatever, some of them with exact radial velocities, some of them just with approximate radial velocities. I only measured about 35 stars from each cluster in full. So I had to kind of extrapolate a little bit from there. Anyway, so you have a few hundred stars do this, right? And then you just say, okay, for each of those stars, what's the closest each one comes to another star? And like you get this big spreadsheet of data that actually says, okay, this guy came the closest to this other guy and it came within 1 parsec or whatever, right? Like you actually get a number for how close every single star came to each other star. And then for each simulation, you just say, great, what's the closest anybody came to anybody, just because that's an exciting result to think about, because the closer it is, the bigger the interaction. It's just a neat thing to look at. And thus you get a minimum separation for that simulation, okay? You do that 10,000 times, and then you get a histogram of what was the most likely minimum separation in across the 10,000 trials. So it's not that there's really like, it's not that there's anything preventing a star from getting closer to another star. It's really that I'm just measuring the statistically most likely closest approach for any two stars anywhere. Hopefully that makes some sense.
Great. We have a question. What is the GUM Nebula? Is it a supernova remnant or some form of stellar wind-blown bubble? And how old do we think it is?
There's a lot of debate on that, and it's actually not fully determined. People are still arguing about it. People are pretty sure at this point that it is an H2 region, powered by the three hot stars, really two now because one of them blew up. People used to think it might be a large supernova remnant, but I think that's in general fallen out of favor, and they've come to prefer the H2, just diffuse H2 region. So I think that's what's prevailing now, but it is still a bit up for debate. As for the age, well, the hot stars themselves, if it is just an H2 region, I think the hot stars themselves are maybe anywhere from 5 to 10 million years, roughly. It's kind of a range. So I guess just based on that, the H2 region would have been glowing for about that long, 5 to 10 million years.
Great. There's a question. Are stars at the center of the galaxy old or young?
That's a good question. Not quite my field. So does star formation happen in that mess over there? I think some of them are old, but I don't know. The ones that are in the plane can be new. I'd have to ask somebody in my college for that one. I actually don't know the age of the ones near the middle. You know what? I think they're old because the bulge is yellow. Yes. Okay. So if you look at a picture of a spiral galaxy, the arms are all blue, and then the middle is yellow. Turns out you only get blue stars if they're young, because blue stars die fast. So just based on that, because we don't really see any blue in the bulge of the spiral where the center of the galaxy is, must be old. Okay, so there's my answer. They're old.
Great. Here's a good question, one that I've actually been interested in as well. Is there any indication our sun formed in a cluster, and has it interacted with other stars? And if so, if it did form in a cluster, do we know where our sibling stars are?
Yes, so that has been a matter of debate for a long time. The sun doesn't really seem to have siblings, which has mystified people for a long time. So one of the new theories, and this is kind of fun because it ties in a little bit with my work. Some of my clusters, they're pretty sparse. I mean, did you see that first one for CG30? I'll just go show it again. There's my presentation. Let's go all the way back to this guy. See that little tiny cluster there? It only has like 20, 30 stars or something. Like it's very few. This cluster was possibly formed in what's called a cometary globule. And if you look, see that little dark blob that's near CG30 IRS4? That's a cometary globule, which it's a lot like a Bok globule, which is just a dense blob of gas that forms a bunch of stars. But cometary globules, they have a comet-like shape because they've been irradiated. So this is another sign of the moderate radiation environment, is these little blobs are actually kind of photo-evaporated into comet-like shapes. These particular blobs can form stars, but they tend to form fewer stars. So they can form small clusters. So one possibility, since our sun doesn't seem to have siblings, is maybe it formed in a cometary globule and was in a small enough cluster that if it was just formed with maybe 10, 20, 30 siblings, that's really not that many in the grand scheme of things. So after having aged for 5.5 billion years, who knows where they went, right? They could be anywhere at this point, and it's hard to keep track of that few stars that formed that long ago. So maybe that's why we can't find the siblings.
Great. Here's also another question that I would have asked if I wasn't co-hosting. Are there similarities between colliding clusters and interacting galaxies? Would the stars in an interacting galaxy be passing close enough to each other to impact local individual star systems?
Maybe. So there are definitely some similarities because you'll get interaction, plain and simple, right? Like at the end of the day, it's really just a different scale, right? You have masses coming close to other masses and gravitationally affecting each other. So in a simple physical sense, yes, they're similar, just at different scales. In a more individual sense, one would think that if you have a galaxy coming through another galaxy, there's a little bit more involved there because galaxies also have a lot of gas, depending on what kind of galaxy it is. So you'll also have star formation events and other fancy stuff, which on the cluster scale, cluster, you really won't get so much, because especially for the ones that I'm looking at, even though they're fairly young, they're no longer gaseous. So you won't get new star formation events, probably not. And then the other thing for galaxies is galaxies are very big. So I would think that a cluster hitting a cluster would really be more likely to have stars pass close to each other, like individual stars, whereas a galaxy hitting a galaxy, it will increase the likelihood of cluster-cluster interaction and thus star-star interaction. But it's sort of a few steps removed, if you see what I'm saying. So because of that larger scale, if you're looking already at a cluster-cluster interaction, you're more likely to see star-star close pass. Whereas if you're looking at galaxy, could happen, and you could maybe like do some study across the several different clusters that might come closer to each other, but it's a bit more of a long shot. It's less definite that you're going to actually have an individual star. Also, good luck with that simulation, because you're talking a lot of stars if you're doing a galaxy interaction.
Yeah, N-body on that would be hilarious.
Oh, no, thank you. I don't have the computing power yet.
Here's a question. The sizes of stars are astounding. Aldebaran, massive but smaller than Betelgeuse smaller than VY Canis Majoris. Is there anyone studying these order of magnitude off the chart massive stars, and do they ever enter into your field of study?
So I'm not really working on massive stars as massive stars, but that is a big field of study, and it's very interesting. Let's see. So yeah, it happens. I really only study the radiation effects of said massive stars, but mine are only right. They're only like 20 solar masses, 10 solar masses. It's still big, but it's certainly not at the crazy upper end, like 100 or even 200. It's none of that. It's also nothing like population 3. If you want to really go crazy thinking about this crazy stuff, you can look at the population 3 stars from way back in the day, back at near the beginning of the universe when things were closer together. Remember, like what I said earlier, back during that time, some people theorize you could have formed like 1,000 solar mass stars, which just sounds ridiculous. Who even knows? And that's because yeah, stuff was closer together, so it might have been possible. There was also less what's called metal, which astronomers have a bizarre definition for, but that may also maybe have affected how big a star you can make. If you just have pure hydrogen and lithium and helium, maybe you can make a bigger one, who knows? But yeah, crazy stuff. But mine, since they were formed only a few million years ago, you're not going to have anything that crazy, and haven't seen anything too large in my particular clusters. But it is a very good field of study, so I encourage you to continue looking into it.
Cool. We have a question. Does the size of a star influence its rate of aging?
Yes, completely. It's mass specifically. So there's a bit of a word use unfortunate happening where size, you could be talking about the radius of the star, or you could be talking about the mass of the star. Mass is the important one. Radius will actually change throughout the star's life. So will mass technically, because it'll tend to lose some mass over time. But radius will actually kind of fluctuate depending on what stage of the star's life it is. Sometimes they bloat out, like during the red giant phase, where they're not more massive, they're just puffier. Okay, so that's just sort of an effect as the star ages. But what determines the time it takes for the star to age is very much its mass. The more mass you have, even though it seems like, oh, I have more hydrogen fuel. No, the more mass you have, the hotter you are, the faster you burn all your fuel, and the sooner you blow up and die. Right. So it's stars are crazy. So the really, really, really massive ones live for like 1 million years. That's pretty short. Good luck even forming a planet during that time, or you have so much radiation you probably can't anyway, right? So yeah, so that's pretty crazy. And then you look at a tiny star like the little red dwarfs, they can live for billions and billions and billions and billions and billions of years. Even though they have less hydrogen, they're cooler, they're smaller, they're less explosive and crazy. Like they burn through what they have much more slowly. So mass is like the property that determines pretty much everything that's going to happen to your star.
Oh, great. Another question, does the interaction between stars have an impact on the Fermi paradox? Does the interaction affect how habitable planets would be?
Yeah, so I would think so. So the it will to an extent. So it won't determine whether or not you can have life, but it'll probably determine whether or not life survives. So if you have those stars interact and you happen to have life, good for you, you have life. That interaction with the other star only takes like a couple million years. Think of our planet, right? It's a few billion years old, right? So it's a pretty brief event when you interact with another star, at least from my initial study of this. This is like the first study of its kind. So we still need more statistics on this, but so far it looks like the interaction with the star tends to be brief, okay? Because it's just in passing, okay? So it won't cause you to have life or not necessarily, but it means that if you get a whole bunch of comets coming at you and you get unlucky and you get a comet swinging into your planet, well, if you had life, you might not afterwards. So that would kind of suck. So I guess in general, it would make it somewhat less likely to find life just because it has such a potential to cause extinctions.
Of course, yeah. Oh, that's wonderful. That brings us to our end of our Q&A session. But thank you so much, Alexandra, for an absolutely amazing talk and a wonderful Q&A session. Very, very interactive and very fun. So thank you so much.
Yeah, thanks for having me. It was fun.
Yeah, lots of fun. We really appreciate your time here. I'd also like to express my gratitude to the amazing astro imagers who generously shared their work with us this evening, and I wish them continued clear skies and some amazing photons. And thank you, a very special thank you to our partner, the Calgary Public Library. Hamza Zorka, thank you very much for hosting us this evening, and thank you to all of you who joined us tonight. I hope you enjoyed it as much as I did. It was very fun. Before we sign off, I'd like to remind all the RASC members about the Members Showcase social that's coming up next month, and look for more details in our Star Seeker. If you have any questions regarding the Calgary Centre of the Royal Astronomical Society of Canada, please feel free to drop into one of our many social media channels. Or send me an email. We'd really love to hear from you. Thanks again, Alexandra, for a wonderful evening, and thanks everybody for joining us. Zorka, if you don't mind to provide us with some final words, and we close out this evening.
Yes, thank you, Alexandra. That was super interesting. Thank you so much for finding the time. And thank you, Simon, and the Royal Astronomical Society of Canada for this wonderful program. And also thanks everyone for joining us. I also would just like to remind everyone that the libraries are still closed at this time for the in-person visit, but you can visit us online, you can order the books and do the curbside pickup. Also, please visit our website for all other programs that we are doing online. And please sign up for some other interesting like this one. And thank you all once again. Have a good night.